All right, so welcome back for section 8.3. In section 8.3, we're going to be we're using hypothesis test about a claim made about the mean of a population. So in this section, we have two things. There's part one and part two of this section. Both of them are going to be testing claims about a population mean, right? In part one, we're going to take a look at the very realistic and common case where the population standard deviation is not known, because that makes sense. If I don't know what the population parameters are and I'm making claims and testing them, then I don't know what the population parameters are. In part two, we'll take a look at, it's a really quick discussion. We'll do like one or two examples where somehow magically we've happen to know the population standard deviation without knowing the population mean. It's weird. We'll talk about it more when we get there. But first off, our objective is to use a hypothesis test about a claim that's made about a population mean. The information, the data, the notation, n's for sample sizes, x bars for sample mean, s's for sample standard deviations, and mu's and mu sub x bars for our population mean, because in a sampling distribution, remember those two values are the same. So the mean of the sampling distribution, the mu sub x bar, works out to be the same as the mean of the population. Okay. Our mathematical requirements are simple random samples and either normal populations or big enough sample sizes, which are essentially the same requirements as when we were doing confidence intervals. Normal distribution that our sample is drawn from, or big enough samples. Right? So if we don't know about normal distribution, we use the condition n for 30. Right? Technically, when you get down in the weeds, if you have a reasonably big enough sample size, it works if the distribution is not far off in normal, right? We're not going to see this. There's not going to be an example where we're going to say, hey, there's 23, can you do it? I'm just saying, in practice, if you had a sample size of 25 or 20, you might look at that and go, well, it's not big enough because 30 is that magic number, but does the population look close to normal? And if it looks close enough, then yeah, we could do it, okay? For us, for our course, we are just going to use that 30. We're going to say 30 is the cutoff. Got to have more. Okay? The math behind the scenes, because we are doing mean testing of an unknown standard deviation, we're going to use that t-test, the same one that we use to calculate our confidence intervals. The math behind the scenes is this business, where the math is going to take the sample data and the hypothesized mean, and it's going to put it into that format. It's going to return a t-value. Now, the same logic is going to apply here as with population proportions. We are going to have a sampling distribution that is going to be modeled by our t, our student curve, right? We're going to have a middle, which is our our mean from our null hypothesis. We're going to have data that is going to give us a t-score, and that t-score is then going to be placed somewhere on that horizontal axis. If that t-score falls into the rejection region, we'll reject the null. If the t-score falls into the fail to reject region, we won't reject. So for example, if we were doing a left tail test, that would be our rejection region. This would be our don't reject region, or fail to reject. So this is the fail to reject. This would be the reject. That's our critical value. Our data is going to give us our test statistic, our standardized test statistic, or just test statistic for short. We're going to plot that. If it falls over here, we reject, and if it falls over here, we fail to reject. Okay? We're not actually going to do that part though. This is going to fall back on p-values again. Because p-values are faster, easier, the calculator does the work for us. We find the p-value and we use the same rules we used before. If p is less than alpha, if the p is low, the null must go. We reject the null hypothesis. If the p is greater than alpha, we fail to reject. Right? It's pretty straightforward, very similar to what we did before. The only thing different is the ones in 8.1 were statements about population proportions. This is going to be a statement about a mean. All right, so let's just dive right into it and take a look at an example. A used car dealer says that the mean price of used cars sold in the last 12 months is at least $2,100 or $21,000. That's our claim, right? Says, claims, mean price, at least $2,100. So the claim is that the mean is at least I kept saying $2,100, $21,000. So we have a claim about a population mean of at least greater than or equal to $21,000. At least would mean that number or bigger. That's why it contains equality. Since it contains equality, that means that our claim is going to be our null hypothesis. Now, I'm going to have the same issue. We're going to have the same issue here that we had before. When we write our pair of hypotheses, we're not going to put in the greater than or equal to. We're just going to say equal to, and that our alternate will be the mean is less than 21,000, right? So that the claim and the alternate end up being complements, right? So our claim here is going to be manifesting or showing up in the null hypothesis. Now we need to gather some data. Now there's a lot of numbers in here, but let's take a look at what's going on here. I've got a random sample of 14 used cars. So my sample size is 14. I'm already worried because I want big samples. This is a small sample. I'm going to run with it and see what happens with the rest of the data when I gather it. I've got a sample mean price of 19,189. Sample mean X bar 19,189. Okay. I got a sample standard deviation of 2,950, and I got an alpha level of 0. Oops, got ahead of myself there. Alpha equals 0.05, and I'm supposed to assume the population is normally distributed. Okay, good. So that means that our small sample's okay because the population of car prices is normally distributed. Okay. So I think I've got everything I need here. Let's check and see. I'm going to go to the same place I went last time, stat tests, but now I'm looking for the proper test to test a claim about a mean when I have sample data. Now here's the key thing. Since the standard deviation that I know is a sample standard deviation, I'm running a t-test, which is option number 2 on my calculator. The t-test, that looks really different. So, one thing that's going to happen when we are running tests about the mean is the calculator is going to say, hey, wait a second. There are 2 ways that your data could be delivered in the problem. One way is the way that we're seeing here, where we are handed the sample statistics. The other way is they could have just given us the 14 car prices, which means they would just give us data as data. Now, since this one gave us data as statistics, and that first option there, I'm going to highlight stats because I know the statistics. I don't have the data. I don't have those 14 car prices. But that's okay. The calculator can still handle it. Mu sub 0. Sub 0 means I'm looking for the equality statement from the null hypothesis, which means my equality statement was 21,000. X bar, my sample, was 19,189. My sample standard DVSX is 2,950. My sample size is 14. And since my alternate hypothesis is a less than, I am running a left tail test. I will then calculate. I get a test statistic, if I were to need that, of negative 2.3, negative 2.296997128, round wherever it needs to be rounded. But more importantly, I got a p-value. I got a p-value of 0.019. Now when I compare my p-value to my alpha, I see that my p is less than my alpha. When p is less than alpha, we must reject the null hypothesis. But the claim was the null hypothesis. So I need to go back to that chart way back up here to figure out what to do. Okay, the data said reject. The claim was the null. So we're going to say that there is sufficient evidence to reject the claim. So back down to here. And I am going to say then that there is enough evidence to reject the claim that the mean price was at least, let's see if I can get it right this time, 21,000. There you go, I got it right. Dollars. Hypothesis testing. Right? It's really pretty straightforward stuff. And luckily for us, the good people at TI have made this so much easier. It wasn't too terribly long ago when these problems were grueling because there was so much work to be done by hand that it was very, very easy to get lost in what you were actually doing. And then you end up with a hot mess. You end up with a problem like this taking 20 or 30 actual calculations to get done. And any mistake anywhere and the whole thing was garbage. Oh, I do not like those days. I am so much happier now. Let's take a look at another one, see if we can make it make sense. Right? All right, so an industrial company claims that the mean pH level of the water in a nearby river is 6.8. Claims mean is 6.8. Mean is 6.8. Right? That's a statement of equality. That means that's the null hypothesis. Our alternate hypothesis then would be that the mean isn't 6.8. Right? Because of that, we're running a two-tailed test. Now we need some data. Right? So we're going to gather some data. The sample mean and standard deviation are 6.7 and 0.35 respectively. So my sample mean is 6.7. My standard deviation is 0.35. Oh, I skipped right over it. 39 water samples. N is 39. That makes me really happy. And I'm happy because it's more than 30. So I don't have to worry about anything as normal. Right? I've also got a significance level, an alpha level of 0.05 in this problem. Now, judging from what I needed last problem, I think we've got all our data we need to run this hypothesis test. So stats, test, t-test, because it's a hypothesis test about a mean where I know sample statistics. So t-test, I'm putting in stats. My mu sub 0 from the null hypothesis, the statement of equality, is 6.8. My sample mean is 6.7. My sample standard deviation is 0.35. My sample size is 39. I'm running a two-tailed test, so I'll make sure I select that. And I'll go ahead and calculate. My test statistic, should I need it, is that negative 1.78. But what I'm really looking for is I'm looking for that p-value. And my p-value is 0.08. Right? That P is greater than alpha. When I compare P with alpha, I see that P is greater than alpha. When P is greater than alpha, we fail to reject the null, right? Remember, our claim was the null, and we're failing to reject the null. So I'll go back and take a look at that little chart. Okay, there's my little chart. Right? The claim was the null. The math failed to reject, so this is our answer. And so there is not enough evidence, there's not sufficient evidence to reject the claim. So down here, okay, so now I can write that up, and I can say that there is not enough evidence to reject the claim that the pH is 6.8. Now, sometimes in this statement that I just made there, someone will actually tuck in the alpha level too. They might say, at a significance level of 0.05, there is not enough evidence to reject the claim. Or maybe they might say, there is not enough evidence to reject the claim that the pH is 6.8 with a significance level of 0.05. They might tuck this in somewhere in that sentence to add in for the reader, not only that it was tested, what was the significance level used. All right. 1, 2, 3, 4. 4 more to take a look at. They're all going to be fairly similar. It's just repetition of the same thing. I'm looking for a claim, trying to build hypotheses, gather some data, run it through the calculator to do the test, let it do the math for us, come up with an answer. Okay. A Department of Motor Vehicles office claims that the mean wait time is less than 14 minutes. So there's my claim. My claim is that the mean is less than 14 minutes. Right? That is a statement of inequality, not equality, which means we're looking at an alternate hypothesis there. So that is the alternate, that the mean is less than 14. So our null would be the mean is 14 or higher. Right? Now let's gather some data. Okay. Random sample of 10 people. Don't like that at all. N is 10. Not good. But okay, all right. Mean wait time at 13 minutes. Sample mean, 13, with a standard deviation of 3.5. So S is 3.5, okay. At an alpha level of 0.1, so alpha is our 10%, 0.1. Test the office's claim. Ooh, yay. Assume the population normally distributed. That makes this okay. Normally 10 is way too small. But since we're supposed to assume the population is normally distributed, life is good, we can make this happen. Okay? So I'm testing a claim about a mean. I have sample statistics, so I'm going to use my t-test again. Stat, test, t-test. I have my statistics. The statement of equality from the null hypothesis puts my mu sub 0 at 14. The sample data tells me my sample mean x bar is 13. My sample standard deviation is 3.5. Make sure I type that in correctly, 3.5. My sample size is 10. And I'm running a left tail test because of the alternate hypothesis. I'm going to go ahead and calculate it. The test statistic, should I need it, is that negative 0.9035 there. But more importantly for us, my p-value is 0.195. Right? When I compare my p-value to my alpha, I see that p is greater than alpha, so we fail to reject the null hypothesis But remember, our claim was the alternate here. So fail to reject, claim is the alternate. Go back to my table. Fail to reject, claim is the alternate. That puts us down here, and we would say that there is not sufficient evidence to support the claim. Okay. Let's see what that means in terms of this. Well, we would say there is not enough evidence to support the claim that the mean wait time is less than 14 minutes at a significance level of 0.10 if you wanted to add that in. This is another one of those ones where it seems kind of kooky if you just look at it. They said it's less than 14. Our data comes back with 13. 13 is less than 14. You would think it would support it. But what ends up happening is it's not low enough for such a small sample to get us into that rejection region, which is where we need to be. We are not far enough left of middle being 14 here, to get us into that rejection region. Right? It also has to do with this being a fairly large standard deviation for a mean of 13. Right. Let's try another one. The Metropolitan Bus Company claims that the mean waiting time for a bus during rush hour is less than 8 minutes. Well, claims mean less than 8 minutes. Mean less than 8 minutes. It doesn't contain equals. That makes it the alternate. So then 8 or bigger would be our null. So our claim is the alternate. Now I need some data. Let's see. Sample of 20, mean of 6.6, standard deviation of 2.1, alpha level 0.01. N is 20. X bar is 6.6. S is 2.1. Alpha is 0.01. Okay. I don't like this, but look at that. We're good. We can assume that it's normally distributed, so we don't care that it's 20. Okay. I'm testing a claim about a population mean, and I have sample statistics. I'm going to run a t-test again. I still have sample statistics. My mu sub 0 is the equality statement from the null hypothesis. That's 8. My x bar is my data. That's 6.6. My SX, my sample standard deviation, in this case is 2.1. My sample size is 20. And I'm running a left tail test again. So I calculate my standardized test statistic, or my test statistic in this case looks like -3 almost, -2.98. But more importantly, I've got a p-value of 0.003. Now when I compare my p-value to my alpha, I see that p is less than alpha. When p is less than alpha, we are going to reject the null, and our claim is the alternate. So I'm going to go back up to my table. I'm rejecting the null. Okay, so let me get rid of this. I'm rejecting the null, and the claim is the alternate, which means that we are going to intersect right here, and we are going to say there is enough evidence, sufficient evidence to support the claim. Okay. So now I'm going to come down here and I'm going to say there is enough evidence to support the claim that the mean wait time is less than 8 minutes. There's an E in there, minutes, at a significant level of 0.01 if you want to add that in. Yay. So the Metro Bus Company said it's less than 8. The data supports that. So we say, hey, look, there's enough evidence. There's data. There's enough evidence, data, to support your claim. Good. All right. I got 2 more that I want to do, and then we'll take a break and come back and do the last section, which is the other case. Okay? All right. Going to start going a little faster because we're getting better at these. A trucking firm suspects that the mean life of a certain tire is less than 35,000 miles. Mean less than 35. To check that claim, so that's our claim. So the claim is that the mean is less than 35,000. Does not contain equality, so it is the alternate hypothesis there. And that our null would then be 35 or bigger. Right? So to check that claim, we're going to get some data, right? So checks 18 tires, mean life of that, 34,450 miles, with a standard deviation of that, 1,200 miles, at a significance level of 0.05, test the trucking firm's claim. So my data is that N is 18, X bar is 34,450, S is 1,200, and we've got an alpha level of 0.05. Okay. All right, I got a problem. That's not enough. And nothing in this problem tells me that I have a normally distributed data set that this sample came from. There's nothing in here that tells me that the population of these tires is normally distributed. So I can't run a test on this because it is not enough data. It is not enough. They need to get me more data because this data is not sufficient to run this test. Right? So this is our first example where we failed. And when I say we failed, I mean the test cannot be run. Now, big picture, there are ways to make this work still. There are statistical methodologies, specifically this thing called bootstrapping, where you can use a undersized data set and repeated sampling from the undersized data set to run hypothesis testing. We're not doing it. It's outside the scope of this course. Okay? All right. So let's take a look at our last example before we end this video. All right, so here's our last example. A school district claims that the number of school days missed by its teachers due to illness is below the national average of mu equals 5. Okay, so this problem is going to be tricky for a couple reasons. One, because this is stated as equality, but what's the claim here? The claim is that it's below the average. So the claim is that they're below average, that their population, meaning their teachers, have a lower mean than the overall national average. Since that statement does not include equality, that really represents the alternate hypothesis, right? That our mean is less than 5, that our null would be that it's 5 or more. Now here's where things get tricky. I've got a random sample of 28 teachers, okay, and they just gave me the data for those 28 teachers. Now, I have to admit something. There's a typo in this problem. We are supposed to assume that it's normally distributed. When I wrote these up, I didn't put it in, and I'm sorry about that. So pretend that it said here at the end that the population was normally distributed. Okay. All right. I don't have data. The only thing I know for certain is that n is 28. But what's x bar? What's s? Okay. I know my alpha is 0.05, but if I don't have these values, how do I make this thing work? Well, the good people at TI thought that this scenario might happen. And so what they've done for us, if they've set it up so we could just take that data as a data set, put it directly into the calculator, and then have the calculator find this, and then run the test for us. So what we're going to have to do is we're going to have to go back to something we did a long time ago when we were finding means of data sets and finding means or standard deviations of data sets. And I need to put that data into a list on my calculator. So I've already got some garbage in there, so I'm going to clear it out. And now what I need to do is I need to put all of that data into there. So I need to put in my 0 and my 3 and my 6 and so on and so forth. So I'm going to pause the video. I'll come back when it's all typed in. Okay, I'm back. I got all the data typed in and I checked it twice because typing the data in is the weak point. That's where mistakes will be made. Okay? Now that I've got the data in, back to stats, over to test, run a t-test. But this time I'm going to say, oh, calculator, you have the data now. 5, the mu sub 0 is still going to be the equality statement from the null hypothesis. But now, just tell it where the data is. I put the data into list 1, and I have a 1 for frequency because it is just simply one data set. It is not a frequency distribution. Every value shows up once. It's a left tail test from the alternate hypothesis. Calculate, and it finds it. And if you needed it, there's the x bar at 3.3. There's the standard deviation at 1.96, right? There's the standardized test statistic at negative 4.5, but more importantly, there's the p-value. Okay? Uh-oh. Now, this is one example, the only example we've seen so far, where it can be a little tricky. Look at that p-value. Do you see the 5.48? But what about the e negative 5 on the end? Scientific notation, that p-value is actually 0.00005. That 5.48 times 10 to the negative 5th means move that decimal point 5 places to the left, which means we're going to have 1, 2, 3, 4 leading zeros. That is a very small p-value. And when I compare that very small p-value to that alpha, what are we looking at here? Well, when p is less than alpha, we reject the null. Now, our claim was the alternate, so what does it mean to reject the null when the claim is the alternate? I don't know, I'll go back and look. I don't have these memorized yet, but that's okay. I'm rejecting the null, the claim is the alternate. This is the same answer as the last one we actually did. There's sufficient evidence to support the claim. So then back down to here, we could say that there is enough evidence to support the claim that the mean absences is less than 5. at a significance level of 0.05 if you wanted to add that. Okay. All right, I'm going to end this video here, and I'll come back and we'll finish Chapter 8, Section 3 in the last video. Have a good one.